all about my least favorite instruction in algebra. The word simplify. The word simplify doesn't tell us much, but the word simplify usually means if you've got fractions, reduce that to lowest terms. If you're able to combine like terms, you probably should. Sometimes simplify means give an answer with no negative exponents, but it's like this great big word, or sorry, it's a teeny word that means a whole lot of different things. So let's get more specific. But before I go there, I want to talk about something else that's going to come up in this next homework assignment. And that's this idea that we can't divide by 0. I'm going to let you in on a little secret. We can divide by almost 0. But the problem that comes up with 0, and I wouldn't take notes on this for a second. If I said that 6 divided by 3 is equal to 2, the reason that this is true, the because part of that, is that 2 times 3 is equal to 6. So the problem with dividing by 0 isn't that there's no answer. The problem is actually that there are an infinite number of correct answers. So if I had something like 5 divided by 0, and I didn't know what that was equal to, but I tried to write out this same because statement, that because statement would look like 0 times something is equal to 5. Can you think of any number that I can multiply 0 by and get 5? I'm going to go with no. So the reason that I can't divide by 0 is that this because statement doesn't work. It doesn't give us some sort of value. But if I flip this around and I had 0 divided by 7, well, if I've got 0 divided by 7 and I wasn't sure what that was equal to, and I wrote out the because statement, that because statement would say 7 times something is equal to 0. This is real clear. There is only one thing I can put in that box. 7 times 0 is equal to 0. So for our purposes in Math D, if I have a number divided by 0, this means I have no solution. Now we're going to develop some fancy calculus tools to deal with a number divided by 0, but for right now, a number divided by 0 means I have no solution, but 0 divided by a number is equal to 0 in Math D. And as far as I can tell, everywhere in calculus. And I was trying to set that equal to some number and solve for this thing. What's important to preserve is that x cannot be 3. We sometimes talk about this as the domain of a function, but here we don't really have a function. We just have an expression. So if I just have an expression, then we talk about the values where there are restrictions on the variable. So that x not equal to 3 is the restriction on the variable. I can have more than one restriction on a variable. So if I had, let's say 5 divided by x squared minus x minus 6, then the restriction on the variable would be that the entire expression in my denominator could not be equal to 0. So I can write that out as x squared minus x minus 6 cannot be equal to 0. For practical reasons, this is not as helpful as having the actual X values that would make this equal to 0. So if I'm asked to find the restrictions on the variable and I have some sort of quadratic term like this, the goal would be to solve this thing by factoring so that I'm setting each of the factors equal to 0. That's why I said we got a lot of factoring in our future today. So x squared minus x minus 6, if I go to factor that, I know that to get the x squared, I need an x and an x. And then to get that 6, I'm thinking about the factors of 6. So I can have 6 and 1, 2, and 3. Well, if I put in 6 and 1, and I do my distributions, I'd have a 6x and a 1x, and I can't make a negative x out of that. But if I put in the 2 and the 3, a 2x and a 3x, I can get a negative x out of that if I make the x negative and the 2 positive. Now that we have this factored, this says I have 2 pieces. They're multiplying together to be equal to 0. So one of these 2 pieces has to be equal to 0. It is totally fine if right now you want to write that out to say x plus 2 is equal to 0, x minus 3 is equal to 0, add a 3 to both sides, subtract a 2 from both sides. But where we want to move to is when you get to this point, you can read off that the values for the restriction on the variable are that x cannot be negative 2 or 3. So that was 30 seconds. Just for like reality time check. That is probably, I would expect in 30 seconds for this problem that for sure you would have recognized that the numerator is the difference of perfect squares, and you'd have the x minus 3, x plus 3 on top. In terms of that denominator, some of you probably had it factored quickly also. I know that to get an x squared, I need an x and an x. And to get that 6, I have that same 2 choices we had in the previous example, 6 and 1 or 2 and 3. I'm trying to get a 5x. Well, I can use, if I put a 6 and a 1 in, I can use a 6x and a 1x to get a 5, but I would need one of them to be negative. And if we look at this and the fact that that's a positive 6, that means they have to have the same sign. So the 6 and the 1 isn't going to work because if they're both negative, then I'd have a negative 7. And if they're both positive, I'd have a positive 7. So I'm going to think about the 2 and the 3 instead. A 2x and a 3x, I can add together to get that 5x we were looking for. When we're at this point, it is super tempting to look at that and say, hey, x plus 3 over x plus 3 is equal to 1. And they cancel out. So this expression is equivalent to x minus 3 over x plus 2, except at the 2 restrictions in my variable. So this is equal to this, except when x equals, and looking at the restrictions in my variable, I want to go back to my original factored form here. So I'm going to have 2 restrictions on this. X cannot be negative 2 or negative 3. That's a really good question. Is there a hole at negative 2? No, something totally different is happening at negative 2. Let's take a minute to explore that because I asked. Okay. So a couple things that I want to point out. If you just put that original function into Desmos, Desmos does not show you the hole. Shame on Desmos or something. And we know we just figured out from doing that algebra that we should have a hole when x equals -3. So even if I zoom in here on x equals -3, Desmos is not going to show me that hole. But if we look at this picture and what's happening at -2, what we actually see happening at -2, we call a vertical asymptote. So that's what's happening at -2. Desmos is going to show you that -2 piece of it. It's just not going to show us that x equals -3 hole. Now let's say that you typed into Desmos the factored version, and we put in x minus 3 divided by x plus 3. Oh wait, is that what it was? X plus 2. You will notice that those two graphs line up perfectly. So they are equivalent, except for that hole that Desmos is not going to show us. So to recap, this factor that cancels out tells me that I have a hole. And the other restriction on the variable that's left over that didn't cancel out is going to give us a vertical asymptote. Vertical asymptote, that guy is a hole. But coming back to this one, if we want to get it factored, the top, it's not an a squared term. So I'm not thinking about having these two factors from a trinomial. Instead, I'm thinking, is there anything that they have in common that we can pull out? And the 10 and the 20 definitely have a 10 in common. So I can pull out the 10 and then I would be left with a plus 2. Because distributing the 10 back in would give me 10a plus 20. On my denominator, I'm actually going to start off the same way. It's not a trinomial. I don't have that like plus or minus an a term. I just have two pieces. So I'm hoping that after I factor something out, that it is that special difference of squares. And when I factor the 5 out, I'm left with a squared minus 4, which is the difference of perfect squares. We can factor that down further. So that I've got 10 times a plus 2 over 5 times a plus 2, a minus 2. Now that we've got it factored, we could pause here and go ahead and write out our restrictions. Because we know that our restrictions are going to come from the factored form before we've simplified anything. So when I look at my restrictions, that's asking the question, what would make the denominator equal to 0? There is a common mistake that students might make if they were working through this problem in a hurry. And I just want to point it out because I think it's equally important to be able to catch your own mistakes is to be able to do the problem correctly the first time. So when I look at this, for if I were in a hurry, I might accidentally write that a cannot be equal to 5. And I see it happen a lot because there's this 5 in the denominator. But what that 5 is saying, if we tried to set this equal to 0, would be that 5 is equal to 0. Not that something is happening with a. And you know what? 5 is never equal to 0, so we don't have to worry about it. I just have to worry about these next two terms where this would lead me to say that a cannot be -2, and this would lead me to say that a cannot be +2. Now that I've got my restrictions, now we can go ahead and simplify this. And sorry, my finger kind of wiped through that a little bit, but a plus 2 over a plus 2, that is going to cancel out to become a big fat 1, and 10 divided by 5 is going to leave me with 2. So my final answer here, I would be looking at 2 over a minus 2. My instructions are the same. Simplify and state the restrictions. Well, when I look at this, I can go straight to stating those restrictions because there's nothing to do with the bottom. It's already a linear term. So I can already write that the restriction is that x cannot be equal to 3. Now we move on to the factoring part. This is the difference of cubes. So this is one of those special factors that you will need to have memorized. This is x cubed minus, and the 27 is secretly 3 cubed, which means that when we write this out, I'm going to have x minus 3. We'll square the x, we'll square the 3, and then what goes in the middle is the opposite sign and a 3x. Whole thing over x minus 3. Just like with the previous problems, we do have a factor that cancels out. So that x minus 3 over x minus 3 is secretly equal to 1. That means that this original expression is equivalent to x squared plus 3x plus 9 everywhere except at the restriction. Same instructions. We're going to simplify this and state the restriction on the domain. And this one's a little bit messier, but it's not actually that bad. So I've got 2x cubed plus 2x squared minus 24x, and the whole thing is over x cubed plus 2x squared minus 8x. In general, when we have cubics, we only have 2 choices for factoring. Either there's something that all the terms have in common that we can factor out, or we would need to be factoring by grouping. I'm going to start by pulling out whatever they might have in common. And then we might still have to go to factoring by grouping, but let's start by pulling out whatever they've got in common. Well, if I look at the numerator, I've got a 2x cubed, a 2x squared, and a negative 24x, which means each of the terms has a 2x that I can factor out. Pulling out that 2x from the numerator, I would be left with, from here, an x squared, from that just an x, and from back here, a negative 12. And then in the denominator, it looks like what I can pull out of each term is an x. When I pull an x out of each term, I'm left with x squared plus 2x minus 8. Now I can get everything factored down even more. In the numerator, I know that to get that x squared, I'm going to need an x and an x. And to get a negative 12, I'm thinking about all of those factors of 12. So if I just list out my pairs of factors for 12, I could have 12 and 1, 6 and 2, 4 and 3. And then trial and error wise, I'm sticking them in and I'm thinking, if I add or subtract these numbers, can I get to a positive x? Well, with 12 and 1, with a 12x and a 1x, I could make a 13 or an 11, but I can't make a 1. With a 6 and 2, I could make an 8 or a 4, but I can't make a 1. With a 4 and a 3, I can make a 1. I just need my 4 to be positive and my 3 to be negative. In the denominator, I'm looking at that x squared plus 2x minus 8. So if this is going to factor, I'm going to need an x and an x. And then I'm thinking about those factors of 8. So to get an 8, I could have an 8 and a 1, or a 4 and a 2. Again, it's negative, so they're going to have opposite signs. So I'm thinking, is there a way I can make a 2x? Well, with an 8 and a 1, I could make a 9 or a 7, but I can't make a 2. With a 4 and a 2, I can make a 2 or a 6. The 2 is going to work for me. I just have to make sure that the 4 is positive. So I'd have a positive 4 and a negative 2. Next up, after we've got all of our factoring done, and I know I'm talking through that factoring kind of quickly, so you can slow me down at any point in time. I am keeping an eye on the chat. But now that we're here, I'm going to look for any of those common, oh, actually, I'm going to pause. Pause. Now that we've got the denominator factored, I might as well go ahead and write out the restrictions. So if I'm coming through and I'm thinking for each term in the denominator, what value of x would make it equal to 0? Well, this x out in front, if we plug in a 0, that would make that equal to 0. For x plus 4, I would be plugging in a negative 4 to make that equal to 0. And for x minus 2, I'd be plugging in a 2 to make that term equal to 0. So now I've got my restrictions. Now I'm ready to simplify my terms. Well, x over x, that's equal to 1. And x plus 4 over x plus 4 is also equal to 1. So my final answer here would be 2 times x minus 3 divided by x minus 2. Yeah, excellent question around why 0 is a restriction this time, but it wasn't in some of our other problems. In that denominator, if I'm thinking, and I'll just come back to this one because I already wrote a bunch, because I already canceled some stuff over there, but even just thinking about this piece of it, if I set this equal to 0, because that's where we're restricted, we can't divide by 0. Any other number, we're usually okay to divide by, but dividing by 0 leads us to no possible solution. So if I set this equal to 0 and I plugged in 0 for x, even though that other stuff would actually, well, let's just plug it in. If I plugged in 0, I'd have 0 squared plus 2 times 0 minus 8. So this term would be equal to negative 8. But when I plug in 0 for x here, I'd still have 0 times negative 8. So it would make the bottom 0. So in terms of, let's think about wholes and asymptotes on this problem, right? So our terms where we have a factor that cancels out, those are going to give me my wholes. So this would have a hole here and a hole here. And any remaining factor in the denominator, that's going to be my vertical asymptote. So this is a fairly common sort of chart, or the way that something might be shown in a textbook. And I'm not just talking about in a math textbook, right? Like, I don't know if any of you are taking Astronomy 10, but this could actually be a chart from an Astronomy 10 textbook. We also see a lot of ratios in chemistry. I'm sure there are ratios in biology. So in this case, the way the question reads, the chart shows the ratio of the diameters of planets in our solar system to the diameter of Earth. If the diameter of Earth is approximately 7,900 miles, use the information to answer the following questions. So the first thing that I want to point out is the order of the words in the sentence. And let me turn on my annotate tools really quickly to point out that this says it's the ratio of it's a ratio of, but it says diameters of planets in the solar system to the diameter of the Earth. Now, the order of the things in that sentence matter. So the diameter of the planet in the solar system is what goes on top. To diameter of the Earth. So we're basically going to keep it in the same order that it was written, starting with that first term in the numerator and the second term in the denominator. So when it says, what is the diameter of Jupiter? Well, when I look at the chart, the ratio is 11.2. So the thing that we're trying to figure out is the diameter, and I'm just going to use D so that I don't type so much. So we're trying to figure out the diameter of Jupiter. The thing that we know is the diameter of the Earth. So we're going to put in the denominator of our fraction is the diameter of the Earth that we were given, which is 7,900 miles. And we know that this whole thing is supposed to be equal to a ratio of 11.2. So if I'm trying to solve for the diameter of Jupiter, and words aside, when I look at this thing, I'm going to use the same skills that I would if this just said X divided by 7,900 is equal to 11.2. I'm going to see a fraction and say, how do I get rid of that fraction? Well, I get rid of that fraction by multiplying both sides by whatever gets rid of the fraction. So I'm going to take both sides and multiply by 7,900. This is definitely a case where it is time to pull out the calculator. I do not want anyone to worry about trying to multiply big numbers in your head. Just grab a calculator. So I'm looking at 11.2 times 7,900, and I get an answer of diameter Jupiter is about 88,480 miles. Good times. We could repeat this process same way for finding the diameter of Neptune or the diameter of Mercury. The only thing we would be changing is what goes over here for the value of the ratio. Pausing for just a second in case there are questions. And then I'm going to stop sharing my screen. Not seeing questions. I'm going to stop sharing my screen. Okay. Another very common place where ratios show up is when we're talking about speed or even acceleration, but we'll start with speed. So this is one that if there are little sayings to memorize it, if you haven't memorized it before, the time has probably come, but we talk about this in a couple of different ways. either as writing this as distance equals rate times time, or rate is equal to distance over time. Now, because you all are headed to calculus, this is usually how this would be taught in an algebra class, but there's a subtlety here. And what this equation really says is that the average rate is equal to the total distance divided by the total time. And I know I'm adding more words in there, but the extra words that I've added are going to be important for calculus. So you might as well get them in your head now. That our average rate is total distance over total time. And we can also swap out that rate for saying the speed or the velocity. And I would say these two terms, speed or velocity, are more likely to be what shows up in calculus, specifically this guy, that our average velocity is the total distance divided by the total time. So as an example, if a train traveled 100 miles in 2 hours, what was the average velocity? That's saying the total distance that it traveled was 100 miles. The total time it took was 2 hours. So my average velocity, which is sometimes written as the average rate of change. That's just a little acronym that we'll see in calculus sometimes, but it means the average velocity. Is equal to that total distance we traveled of 100 miles divided by the total time, 2 hours. And we generally want to simplify that ratio if we can. So 100 divided by 2 is going to be 50. And then we have a specific abbreviation for miles divided by hours. Because it shows up so often, it's going to be on the speedometer of your car. It's going to show up on signage on the freeway. When we say 50, we write the abbreviation MPH, meaning miles per hour. But I'm going to approach it in sort of if I were reading this mathematically, what would I write down? So first of all, when I approach a word problem, I start from the question mark and I figure out what the question word is. So if I work backwards from that question mark, blah, 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 where's the actual question word? That's the how. And how far is asking me for a distance. So that's what I'm looking for a final answer. I know I'm trying to find a distance. If I look at the rest of that statement, the in 40 minutes, well, 40 minutes is giving me something that is a time. So I might go straight to, oh, I know how distance and time are related. I know that distance is equal to the rate times the time. So if I want to find the distance and I know the time, I must need to solve for the rate. So now I'm going to jump to the beginning of the problem and see if anything in the problem has given me a rate. So the distance I travel on my bike is proportional to the time I spend riding. that phrase is proportional to does show up for us in mathiness, and is proportional to means equals a constant times. So even if I hadn't remembered that distance equals rate times time as a formula, I've given us enough information in that first sentence to write down this equation, because the distance and then is proportional to means equals a constant times, and then is proportional to the time. So distance equals a constant times time. So that first sentence is telling us the same thing as distance equals rate times time. Okay, onward to my second sentence. When I ride for 30 minutes, I travel 8 miles. Well, that's enough to let us find that constant of proportionality, or the rate that we need to plug in down here. So if I use that second piece, 30 minutes, so that's a t equals 30. And I traveled 8 miles. So I know that the 8 miles is equal to some constant times 30, or that constant is equal to 8 divided by 30. And that is the same as the rate that I would need to come up with a final answer down here. Because I'm running out of a little bit of space on the board, I'm gonna go straight to plugging stuff in. So that distance that we're looking for is equal to that rate of 8 miles per 30 minutes times my time of 40 minutes. A couple of things. My units of minutes over minutes, those are going to cancel out. But also, if I can, I want to simplify the ratios as much as possible. So for sure, 40 and 30 are both divisible by 10. So I can, at the very least, turn that into a 4 over 3. I am looking at 8 times 4 divided by 3. And the units that are going to remain are miles. So I'm going to take that one more step and say 8 times 4 is 32. So that's 32 over 3 miles. Now, for practical purposes, even without a calculator, we should look at that and say, that's close to 11 miles. That's the level of number sense that we hope to get, right? I can say 32 over 3 is somewhere between 10 and 11 miles, because 10 miles would be 30 over 3, 11 miles would be 33 over 3. So that's somewhere between 10 and 11. Part of the reason that I'm like pointing out that number sense piece of this is when you go to take the placement exam, to retake that math placement exam, we know the time is a challenge. Well, if it's multiple choice, I can probably pick the answer that's between 10 and 11 without reaching for the calculator.